Okay, so we started last time with talking about hypothesis testing. It is the most difficult subject for us in statistics that we have in this class in general, though we do it in a number of different situations. I will say the last couple sections of chapter 8, I forgot to mention this last time, are not something that we're going to cover. We're not going to cover doing hypothesis testing about variances in this class. If you take applied stats, we'll talk about that in that class. We also want to do hypothesis testing about medians. We will do that in applied stats instead. But we will eventually, starting a little bit today, maybe even a fair amount today, start chapter 9, even though that won't be on your test that I told you about, because it will give us another way to illustrate both confidence intervals and hypothesis testing in a different situation. So let's start by looking at one of the homework problems that I gave you some hints about last time at the end, but we didn't have a ton of time to go into depth. But this was a homework problem. It would be good to go into depth on it some more again, just to make sure that you get it and understand what's going on here. So let's look at it a little closer here. So this is the problem about brake pads and titanium in brake pads, and the percentage should not exceed 5%. A study is conducted to detect a situation in which the mean percentage, emphasis on the word mean. So we are talking about doing hypothesis testing about a mean, even though the mean is a percentage, that's a little confusing, exceeds 5%. Right? We don't want it to be bigger. It should not exceed 5%, but we're trying to test if it does. So that means our research hypothesis, the alternative hypothesis, is that the mean is bigger than 5%. And the null would be the opposite of that. The problem says, go ahead and set up your hypotheses. Discuss the practical consequences of making type 1 and type 2 errors. And then actually do the test, finding something called a p-value, which I only briefly introduced last time, but we'll reinforce here today. So again, technically speaking, and I do put this on the exam in at least one problem, I want you to describe the meaning of the parameters that you're testing. And in this case, we're testing, well, one parameter. Mu is by definition, what problem number is this? And this is number 31. Mu is the mean percentage of titanium in the brake pads, in all brake pads. I don't remember if this was like for a particular model of brake pad or a particular car or something like that. Okay, I guess they're just talking about all cars' brake pads. All brake pads for all cars, okay? That's a population parameter. It's something that you'd like to know about. You don't want it to exceed 5%, 0.05. We're doing inference. We're trying to say something about a population parameter in this case, based on information from a sample, from a random sample. The null hypothesis and the alternative hypothesis can be written down. And again, start with the alternative. We don't want it to exceed 5%, but maybe we think it does exceed 5%. So the research hypothesis is that mu is bigger than 0.05. That's the alternative hypothesis. Our book calls it H1. Some books call it HA for alternative. That's an A there. The null hypothesis, technically speaking, is the opposite of that, which would be mu is less than or equal to 0.05. Though, as I emphasized last time, it's simplest to treat this in the case where you have equality. And we typically do just write an equal sign. It's introduced as being the opposite of the alternative, and that's technically correct. But for simplicity, we write it with an equal sign in almost every situation, okay? Called a simple hypothesis. And you even had one homework problem that emphasized why that's good enough. And I'll talk about that as we go. Why is it good enough to just consider the boundary case where mu equals 0.05 exactly as your null hypothesis? Even though you might say the chances of the null being true are practically zero, right? What are the chances that mu is exactly 0.05? Probably zero. So in a sense, it doesn't make sense to call this the null hypothesis, but we do anyway to keep it simple. And we give it the benefit of the doubt. That's always the approach you take. Just like a courtroom, you're giving the defendant the assumption of innocence, innocent until proven guilty. It's just like that kind of philosophy. You may or may not want the alternative to be true. It depends on who you are. As a prosecuting attorney, and you really feel like that defendant is guilty, you may want the alternative to be true. You may want them to be guilty and you want to prove they're guilty. Maybe your job is on the line, I don't know. That may or may not be a good reason, but on the other hand, some people want the null to be true. Which one is true? Is the null true or the alternative true? You can't really ever say for sure. You understand that? You really can't say for sure. You only have strength of evidence against the null or lack of strength of evidence against the null. That's what you really end up getting. And I'll say it again. Nobody can assess the probability that the null is true or that the null is false. And likewise, the probability that the alternative is true or that the alternative is false. That's impossible. Nobody can do that. And that's not what a p-value is. P-value is a probability, but it's a different probability. Nobody can figure out the probability that the null is true or false. If somebody tells you they can, they're wrong. They're lying or they're misinformed. Okay? Anyway, after that little spiel, we go on here. Part B, discuss the practical consequences of making a type 1 or type 2 error. Type 1 error means reject the null when it's true. In this case, say the percentage of titanium is bigger than 5% when it's really not. So the practical consequences, well, I think for sake of time, I won't bother writing it out. I'll just say it. You think there's more titanium than there really is. So what would that mean? Maybe you think it's more dangerous than it really is. You think more cars have too much titanium in their brake pads than they really do, and so that's a hazard, and it needs, government intervention. So you spend money on government intervention when you really didn't need to, is one way to look at it. That would be the practical consequence of a type 1 error. Type 2 error, you fail to reject the null when you should have. The null is false, the alternative is true, but you did not reject the null. So that gives you the impression that things are fine when they're really not. The brake pads have more titanium than you think they do, maybe a dangerous amount of titanium when you think everything's fine. And so that leads you to not intervening when really you should, and that causes brake failures, it causes accidents, people die. Okay, you can hypothesize all sorts of consequences of these things. Both type 1 and type 2 errors are not good. They're errors. They're not math errors. They're errors in decisions that you make to reject the null or not. Stop me if you want me to clarify anything, by the way. This is hard stuff to get your mind around at first here. Part C, a sample of 100 brake pads yields a mean percentage of X bar equals 0.051. Just barely bigger than 0.05. I mean, that's so much of a small difference between 0.05. You might say it's, even if we reject the null, it's hardly worth rejecting the null. We're assuming the sample standard, the population standard deviation, is 0.008. That sounds not realistic, doesn't it? Why would we know the population standard deviation if we don't know the population mean? Right? This is just like with confidence intervals. When we first introducing the subject, we pretend we know the population standard deviation or variance just for the sake of keeping the subject simpler, but it's not realistic. We're pretending we know sigma here, even though it's not realistic because it keeps the subject simpler at the moment. We get more realistic for this subject for means in chapter 10. And just like we did for confidence intervals, we use the t-distribution in chapter 10. But for the sake of keeping things as simple as possible, assume we know the standard deviation of the population, a parameter. This says find the p-value. So I just hinted at what the p-value was and wanted you to also do reading to help you figure this problem out. What is the p-value? Okay, this is worth writing once. The p-value in general well, it is a probability. That's why it's called a p-value. It's the probability of what? Of observing a test statistic for your hypothesis test. What is the test statistic? There's lots of things it could be. X bar, maybe converting X bar to Z, maybe T, a t-distribution. There's lots of things the test statistic can be. There's actually, when you get into stats enough, there's like hundreds of them. Probability of observing a test statistic as extreme or more extreme as what you actually observed when you did the test, when you did the sample and computed your test statistic, under the assumption that the null hypothesis is true. It's the probability of observing a test statistic as extreme or more extreme as what you actually observed under the assumption that the null hypothesis is true. It is not the probability that the null hypothesis is true, which is what some people think. That was the thing I said 5 minutes ago that nobody can tell you the answer for. We do reject the null hypothesis. We tend to reject the null hypothesis when we get a small p-value. Like, for example, 0.05 or smaller, say. If I say the p-value is 0.05, I'm not saying the probability that the null hypothesis is true is 5%. That's not what I'm saying. Again, people misunderstand it and think that's what it means. It does not. Nobody can say what that probability is. It's not even a well-defined probability question, you might say. To figure out the p-value, we assume the null hypothesis is true. We give it the benefit of the doubt. And we say, what are the chances of getting these data and these test statistics under the assumption that the null hypothesis is true? And if that probability is small, if it's unlikely to observe these data by chance when the null is true, then we say, hey, we think the null is false. That's the logic. Say it again. Yeah. If we get a small p-value, like, for example, 5% or smaller, that's a commonly used number, though it is arbitrary. Get a small p-value for your test, 1%. You're happy, right? You can reject the null, you can publish your paper, they'll accept it in the journal. Because I got a significant test, I rejected the null, which is what researchers usually want to do. What have they really done? In saying the p-value is small, they've said, if the null is true, it's unlikely that I'm going to observe this. But hey, I did observe this, so I think the null is false. I reject it. I have observed something very rare if I assume the null is true. Because that observation is rare, I therefore think the null is false. I reject it. That's not a foolproof method, right? You could have observed something rare when the null is true. Low probability things do occur sometimes. 5% chance is 1 out of 20 times. Still occurs. If you got a 1 in 20 chance of getting some sickness, that means out of 1,000 people, about 50 people have the sickness, right? It happens. So the null still could be true. You're going to reject it anyway, but it still could be true. You might make a type 1 error. What does as extreme or more extreme mean? It means with respect to the direction of the alternative hypothesis. With respect to the direction, I'll put in quotes because it's not really always a true direction of the alternative hypothesis. If it's a right-tailed test, like this one is, right-tailed test, the p-value is an area to the right of something, as extreme or more extreme in the greater than direction. If it's a left-tailed test, if this were a less than sign there and this were a greater than or equal to sign, that would be a left-tailed test. Then we're finding an area to the left of something. It's a left-tailed test, less than or equal to. As extreme or more extreme means less than or equal to. If it's a two-tailed test, which you would have to put an equal sign for the null there and a not equal sign for the alternative, then is as extreme or more extreme in either direction. Effectively, in cases of symmetry, like a normal curve, you need to take a one-tailed p-value and double it, is what you need to do. Hard to say what the direction means for a two-tailed test. That's why I put direction in quotes. It's also sometimes the case that there's really no parameter you're really trying to test so much as just finding a p-value. That'll become clear if you take applied stats, actually. We'll do some examples, something called a chi-squared test for that. So what does this turn out in this problem? What did we actually observe? We observed a sample statistic, x bar equals 0.051. It's a right-tailed test, so as extreme or more extreme means greater than or equal to 0.051. So for this example, probability that, call it capital X bar, not lowercase x bar, is greater than or equal to the lowercase x bar, the observed sample mean that we found, 0.051. Assuming the null is true, I'm going to go ahead and write this as a conditional probability. Assuming mu is that we take the simple hypothesis here, mu is equal to 0.05, not less than equal to 0.05. What if mu really is less than 0.05? What if it's 0.04 or 0.03? You had a problem related to that concept. And what happens is if mu really is less than 0.05, like 0.04 or 0.03, you actually get smaller probabilities here. So by choosing the boundary value, 0.05, you're making the p-value as big as possible, which is good from a philosophical standpoint, because even though you may want to reject the null, you technically should make it harder on yourself to reject the null. That's the ethical way to approach things. You don't want to reject the null. You may want to reject the null, but you don't want to unless you have strong evidence. You don't want to be wrong. You don't want to make a type 1 error. You may want to reject the null, but only if you have strong evidence. But maybe you think you will get strong evidence. So that's what's as extreme or more extreme, X bar being our test statistic. But we can also think of Z as our test statistic because we can convert this to a Z. Now, you don't always do this on your homework, right? You're used to using your technology and not necessarily using the table. And we use normal CDF and not necessarily using standard normal. Mu is 0, sigma is 1. However, it is good practice to emphasize that we can relate this to a Z statistic because the value we're about to compute will even call little z, the observed value of capital Z. I won't write it here initially, but you have to standardize, you have to subtract the mean. Here's where we're using the assumption that mu is 0.05. Subtract the assumed value of mu. I won't bother writing this as a conditional probability anymore. Technically, it still is, but I won't bother writing the vertical line anymore. I have to divide by the standard deviation. What does that mean? Do I divide by 0.008? Some people saying yes. I see some people saying no. You divide by not sigma, but sigma over square root of n. Why? Well, what is that here? N is 100. That is sigma over square root of n. Why am I doing that? It's because of what the sampling distribution of X bar is. That's what I'm using implicitly here. I didn't say that until now. In thinking about this, I'm assuming X bar is at least approximately normal with a mean of 0.05 and a standard deviation not of sigma, but of sigma over square root of n, and therefore a variance of sigma squared over n. Is X bar exactly normal? Well, if the population is exactly normal, then X bar is exactly normal. That's our cornerstone theorem. Is the population exactly normal? Technically, it can't be because X bar, for example, can't be negative, whereas normal variables can theoretically take on any value, including negative values. So really, this is more of an application of the central limit theorem, and it's more that X bar is approximately normal, but you know, n is 100. That's reasonably large here in most contexts, and at least as if the original population is close to normal. This is probably more of an approximation, but it's a good approximation. We feel confident. Of course, square root of 100 is 10. So this is 0.0008. So I have 0.001 divided by 0.0008 gives me 1.25. Now use technology or table in the back of the book. I'll use technology here. 1 minus the CDF, normal CDF. I'm using a standard normal now. Of course, I didn't have to do 1 minus since I have a lower and upper, but my lower is set effectively to minus infinity, so that'll be easier. It's like the p-value is approximately 0.106. Small, but not outlandishly small, you might say. Is it small enough to reject the null? It's actually up to you. The answer to reject the null is actually a matter of opinion. Hey, you're the one making the decision anyway. If you're desperate to reject that null, you look at that p-value and you say, that's small enough for me. Of course, you have to live with the consequences of a type 1 error if you do. And if that's not small enough for your boss, maybe your boss fires you because you rejected the null and ultimately it was realized you made a type 1 error, though I don't know how you know that for sure. Because again, nobody typically knows for sure what the true answer is. If you're more careful and you like going with the 5% as your definition of small, then you'd say that's not small enough. I fail to reject the null. Doesn't mean you necessarily accept the null. Doesn't mean you necessarily think the null is true. You just didn't have strong enough evidence against it. That's all. As a prosecutor, doesn't mean you think the defendant is innocent. You just didn't convict them. Didn't have a good enough argument, didn't have good enough evidence. Okay. These comments that I'm making are the reality of how you want to think about this stuff. Doing more than just calculations just to get an answer so you can go on to the next problem or to the next assignment, but so you actually understand how people think about this stuff and use it. Question?
So is alpha also?
No, but it's related to alpha. If you have an alpha. Now that brings up another issue. I called the title of this slide significance testing instead of hypothesis testing. There is a reason for that, but I haven't mentioned why yet. So hypothesis, in both hypothesis testing and significance testing, you are doing hypothesis testing. It's the same kind of setup, okay? In classical hypothesis testing, where you have this alpha, this level of significance, alpha is called a level of significance. In classical hypothesis testing, which people in the old days would have said is the more honest way to approach things, you decide on what the level of significance is ahead of time. People often pick 5%. But if you want the chances of making a type 1 error to be smaller, you pick a smaller value of alpha, like say 1%. Based on that value of alpha, you then find the rejection region. The critical region, the values of x that lead to rejecting the null, like was an example in the book. And we went over an example last time, similar to the book. There's a homework problem about it too. Not finding it. Well, let's quick look at the example in the book. It's about the headlights. Yeah, you had a homework problem about this too. They say, let us design a test so that alpha, the probability of making a type 1 error, rejecting the null when p is equal to 0.5, is about 0.05. So they're setting alpha ahead of time, and in so doing, and then doing this calculation, they figure out, since this number is pretty close to 0.05, they effectively treat the rejection region, the values of x, number of cars in a sample of size 20 that have misaimed headlights, that lead to rejecting the null to be this set of numbers. This is the rejection region or critical region for the test. And yeah, they're just trying to do an approximate calculation. Yep. They could have said take alpha to be 0.06. That's closer to 0.06. That may have been a better approach, but I think they just wanted to use 5%. So then you do the rejection region, and then you actually observe your value of x. How many cars out of 20 have misaimed headlights? If x is in the set, then you reject the null. Nothing about a p-value here. That's the classical approach, and that's called hypothesis testing. You might say it's more honest because you're deciding ahead of time what your probability of type 1 error is. Whereas with the significance testing approach, you don't necessarily find your rejection or critical region. Instead, you just find the p-value and you say, hey, here's my p-value, and based on this p-value, I'm going to reject the null or not. And it's up to your opinion, your judgment, as to whether or not that's small enough p-value for you. And your decision might get you fired or not, maybe. I don't want to project too much into your future, but or get you a promotion, perhaps. Look at that positively. From a researcher standpoint, when people are writing scientific papers using statistical testing like this, they don't necessarily say I reject the null, or they may not say I don't reject the null, I fail to reject. They may just say the p-value and leave it at that, and leave it to the reader to decide, or leave it to the scientific community to decide, and probably not just based on that one research paper, but other people's, right? It's not just one bit of evidence. It's the weight of lots of bits of evidence that makes people have an opinion one way or another about something, especially in fields like psychology and sociology and stuff, maybe less so in physics and chemistry. Okay, it's the weight of evidence of lots of research reports that convince people one way or the other. And this is called significance testing, even though it is still hypothesis testing. And you say, when you see a p-value like this, well, if you do have an alpha, you can relate them. You would say, if, for example, alpha is 20% for some reason, though I don't know anybody who would do that, you'd say it is statistically significant at the 20% level if alpha is 20%, because it's less than 20%. If alpha were 10% or 5% or 1%, more common alphas, then this is not less than any of those, and you would say it's not statistically significant at those levels. You say it's statistically significant when the p-value is less than alpha, and it's not statistically significant when the p-value is not less than alpha. Another question?
Well, so I guess what I was trying to get at with my original question, one example is sound approach. Yes, in fact, sound. Maybe example of what you just asked when we so we're rejecting the alpha.
Mm-hmm.
Finding a problem. It's like 0.0577. So if we say that alpha is 0.0577 in that,
You're typically given alpha. You don't decide it in the problems. Now, in real life, you would decide alpha, but you remember which problem you're talking about? $29? Okay, 29 is actually the problem about where the main point of the problem is to illustrate that if you assume P satisfies the null hypothesis, but is further away from the boundary value, you get smaller.
it was 25A.
Okay, 25A. Okay, so we're testing.
So it's fine if we're looking at the critical region is 10, 11, 12, 13, 14, 15. Back to look at all equals 0.0.
Yeah, probably it's a very rough approximation is my guess. Let's just double check the calculations. So we're talking about, so the null, P is less than or equal to 0.4. If we took the boundary value of 0.4, and okay, using binomial distribution, binomial CDF. N is 15. We assume P is 0.4. And what'd you say the answer was in the back of the book for part A?
For the critical region,
Yeah,
greater than or equal to 10.
greater than or equal to 10. So if I put 9 here, and I'm computing 1 minus the probability that X is less than or equal to 9, that's the same as probability that X is greater than or equal to 10. This probably should be in the rough ballpark of 0.05. Is that what they put in the back of the book? Yeah, so there is very much ballpark here.
So which do we say though is alpha? Say it's the 0.338.
Technically speaking, it's this, yes.
Oh, it is. Okay.
But they're just trying to give you the rough idea of it here. A roughly 5% test. They're being very rough.
Okay, and then when you actually do the calculation, times the probability, that's the actual alpha.
Based on the critical region that they said was the answer, yes. This is the true alpha. As we talked about on last time, well, you can find the probability of a type 2 error and something called the power of a test as well when you know the critical region, when you know alpha. In this problem, we were not given a critical region. But let's go ahead and modify the problem a little bit. And let's say I decide on alpha to be 0.05. And let me figure out the critical region, and then I'll use that critical region to figure out probability of a type 2 error and power. Okay, so I'm going to use that level of significance. So what am I after here? I'm after looking really for Z sub 0.05 first. That would be a Z value where the area to the right is 0.05. This is a right-tailed test. So I want to think about a positive Z value, relatively high, where the area to the right of it is 0.05 approximately. Looking in the table, for 0.95, these two are equally close. I see Z is 1.64 and 1.65. I think I'll just split the difference and say 1.645. Actually, I think it's closer to 1.646. Maybe I should use calculator just to be a little more clear there. Go to my distributions menu and use inv norm, area 0.95 for standard normal. Actually, it is closer to 1.645. Okay, wrong. 1.645. So in terms of the Z value, the critical region is to the right of 1.645. You can picture it like that. You could figure out what that means in terms of X bar, working backwards. What does that mean in terms of X bar? X bar minus 0.05, if I assume the null is true, just like I did back up here. Don't be confused by the fact that both of these are 0.05. That's just a coincidence. That's the level of significance. That's the null value of mu for the titanium. I'm still in the titanium here. Divided by the 0.0008. When is this greater than or equal to 1.645? I can solve this inequality for X bar. Multiply by both sides by 0.0008. Then add 0.05 to both sides. This is equivalent to saying X bar is greater than or equal to 0.051316. Let's go ahead and use that many decimal places. In other words, the critical region for a right-tailed test in this situation at the 5% level of significance in terms of X bar is 0.051316 or greater. I could then use this, if I asked you to, you should be able to use this to figure out the probability of a type 2 error or the power of a test, and they're related, remember. They're opposites, really. Let's think about it in terms of power first. The power of the test. Think of it in terms of a prosecuting attorney. As a prosecuting attorney, you want to convict the defendant if they truly are guilty. You want to have power to do that. You want to be able to marshal the evidence and your arguments to convict them if they truly are guilty. Probability of correctly rejecting the null when the null is false. Being in the critical rejection region. When the null is false, when the alternative is true. But wait a minute. The alternative includes infinitely many values of mu. Which one do you pick? It's up to you. I'm being serious. The choice is up to you. But how do you decide? Maybe you pick mu is 0.052, but is that an arbitrary choice? Yeah, it is arbitrary, but there can be a logic behind it. What you typically want to do is you want to typically pick a minimal value, well, in the right-tailed case at least, a minimal value of the alternative that is somehow important to you. If for this titanium, it's important that you be able to detect when mu is really 0.052 or larger, if that's the truth. Then you would like this power to be relatively large. You would hope this is relatively large. Maybe I shouldn't pick 0.052. I think this is going to be small. Let me pick something different. Let me pick 0.0. Let me pick it so that it's a bit bigger. 0.0505. Okay, that's going to make the power a bit bigger. And that again, in reality, in real life, that seems like such a small difference from 5%. It's like hardly worth thinking about. But we're not really thinking about practical consequences here. I'm just trying to get an answer. Convert to z, but now subtract the new assumed value of mu. Actually, it'll be bigger if mu is further away. Maybe I should go back to the original. Let's go back to 0.052. Sorry. This is still dividing by 0.0008. Okay, what's the numerator of that fraction? Subtract 0.052. We get a negative number. That's okay. Divide by 0.0008. This is approximately probability that z is greater than or equal to negative 0.855. And I'll go ahead and have 3 digits, even though that's not in the table, because we have the calculator. Z is greater than, that's going to be higher than 50%. It's going to be 1 minus normal CDF negative 0.855 there. I'm doing 1 minus that. That's going to be bigger than 0.5. It's going to be about 0.8, which, to tell you the truth, is typically a minimal power that people aim for. Is they like when the power is 80% or higher. But again, that's kind of an arbitrary choice. And that would mean the probability of a type 2 error is 1 minus that, about 20%. Beta. Probability of type 2 error, if you assume mu is 0.052. But if you assume mu is something different, you get different answers. It depends on what you assume for the alternative. Though again, you want to assume sort of a minimal alternative value that you would like to be able to reject if that truly is, if that alternative value is truly the truth. Take a stretch break. This is a lot to take in. For the rest of the class today, we're going to talk about these Same idea as confidence intervals and hypothesis testing at the beginning of chapter 9 for proportions. The details are different, but the overall big concepts are the same. Confidence intervals are still interval estimates for population parameters. And hypothesis testing, we're still doing right-tailed test, left-tailed test, or two-tailed test, but for different population parameters. Not a mean, but instead a population proportion is what we're about to do. All right. This is a confidence interval problem. So confidence intervals are, when you get down to it, you realize they're easier than hypothesis testing. Not nearly so intricate in all their details. I will tell you that people who both study and use statistics debate about all this kind of stuff all the time. There are people out there who just don't like doing hypothesis testing at all. They think nobody should do it. And you can find articles about this. There was actually a big article a couple of years ago about it in a very important science magazine. I think it was maybe even a magazine called Science, where they were talking about they should do away with hypothesis testing. And they phrase it in terms of p-values. They should do away with p-values and statistical significance. Do I think that? No, I think it has its uses, but it can be misused. To avoid misusing it, you need to truly understand it. And lots of people use hypothesis testing and p-values without truly understanding it. There are lots of people who think, even many scientists and engineers who think the p-value is the probability that the null hypothesis is true. No, nobody knows that. Just wrong, okay? But that's sort of the intuitive way to think about it. And people think that that's the case, but it's not. You can search for videos of people, scientists being interviewed, asking them what does a p-value mean, and most of them can't say what it means, okay? And that's not to denigrate them, it's just reality that people use stuff they don't understand all the time. And it does lead to misuse sometimes. All right, anyway, here we go. A problem that says a survey of companies using industrial robots showed that 200 robots in use, 48 were used for unloading and unloading, as opposed to some other use. Find a 95% confidence interval for P, the proportion of robots currently being used for loading and unloading in the entire population. You know, maybe for extra emphasis, they should have put the word all in there, the proportion of all industrial robots. This is a population parameter. It's described as a proportion, and that's certainly fine. You could also think of it as a probability. Like, what's the probability that a randomly chosen robot will be used for loading and unloading? It's fortunate that probability and proportion both start with P. Just like it's fortunate that population parameter both start with P. And sample and statistic both start with S. It's so fortunate. What are the chances? So let's go ahead and do part A here without doing part B. And it is a formula. I'll write down the formula. I'm not going to fully explain the formula, but we can maybe make some sense out of it. A 100 times 1 minus alpha % confidence interval to estimate a population proportion P Here's another reason why maybe it's better to think of P as a probability instead of a proportion, because there are some situations where you might call it, say your population is actually infinite. And so how do you compute a proportion if the population is infinite? You'd be dividing by infinity. Can I think of an example? Yeah, I can actually. Flipping a coin. What's the proportion of heads? What's the population proportion of heads? Well, in theory, you could flip a coin forever and ever, right? Infinitely many times if you could do that, literally. What's the proportion of heads? 50%? Well, how do you, wouldn't it be like infinitely many heads divided by infinitely many flips? How does that equal 0.5? So it's probably better to call it a probability, but we do still call it a proportion. Anyway, the formula is this. Your point estimator is p hat. What's p hat? It's the proportion from your sample. Sample proportion. And samples are always finite in size. And if you're thinking of the number of things you're counting as being X, number of successes, say in this case with the robots, number of robots that do loading and unloading, you would take X and divide by the sample size. Very simple formula. That's your point estimator, plus or minus a margin of error. Dr. Wetzel, I always like to call it E first. Some books call it M. Our book actually calls it D or M for margin of error, or D for maybe distance. But what does E equal? Is a special Z value, Z sub alpha over 2, times a standard deviation of something you could call a sampling distribution. Not a sampling distribution for X bar, but a sampling distribution for P hat. And that turns out to equal square root of P hat times 1 minus P hat over N. Where in the world does that come from? Actually, it's not the true standard deviation of the sampling distribution. It's an approximation for it. An approximation for sigma sub P hat, the standard deviation of P hat, or you could say of its sampling distribution. P hat is a statistic. If you think of X as a statistic obtained from a sample, it's a little different than how we were thinking about random samples and statistics before. This X actually can be thought of as a sum, and X over N can be thought of as a mean. But to think of it in such a way, you have to be careful. Say you're flipping a coin. Each time you flip the coin one time, it's either heads or it's tails. If heads is success, then the value of X for that one flip is 1, and the value of X for that one flip is, if it's tails, the value is 0. I probably shouldn't have called that X. I should have called it maybe X1. When I flip a coin n times, it's like I'm flipping a coin one time n times. Isn't that a deep thought? When you flip a coin n times, like 20 times, That means you flipped it once 20 times. And X, the total number of heads, maybe you get 12 heads out of 20 flips, can be thought of as a sum of a bunch of zeros and ones. 1 for every time you got a heads, 0 for every time you got a tails. And therefore, this can be thought of as a mean, but we're calling it a proportion. And therefore, it can be thought of as a sample statistic. As a sample statistic, it's got a distribution, a PDF, a CDF, etc. And we're saying the standard deviation of that PDF is approximated by this. What would it be exactly? It would be exactly this if you used P instead of P hat. I should probably, instead of calling it an approximation, I should probably call it an estimator, because it really is a statistic. It becomes an approximation when I actually have a sample and compute P hat and observe value P hat. But why is it this? Why is it this formula? That's what I don't want to take the time to get into. It's related to standard deviations of binomials, actually. It's at the derivations at the beginning of chapter 9. Yeah, the first 4 pages or so is the derivation of this formula in chapter 9. Let's use it. Okay, so that's the abstract formula in terms of estimators. But now we want to use it based on this particular observed sample, where there were 48 successes out of a sample of size 200. So for this problem, which is chapter 9, number 4, the observed value of P hat is 48 out of 200, 0.24 or 24%. So the answer for the confidence interval, if we're after 95% confidence, which I believe is what we're after here, right? 95%. Yep. Is 0.24 plus or minus our favorite number, 1.96. Remember, that's Z sub 0.025, which is 0.05 over 2. Alpha is 0.05 here. By the way, the alpha used in the confidence level expression is related to an alpha for a certain hypothesis test. After we finish the problem, I'll talk about that a little bit more. Plug into that formula too. Square root of 0.24 times 1 minus 0.24 is 0.76 divided by 200. .24 times 0.76 divided by 200. Oftentimes, the thing under the square root does end up being a pretty small number. Take its square root, it's still small, but not as small. Multiply by 1.96. Looks like our confidence interval in plus or minus notation is 0.24 plus or minus about 0.06. And if I am thinking about significant digits, I should probably keep the same number here. In interval notation, you could write 0.18 to 0.30. And I don't care if you use an open interval notation or closed interval notation, it's not a big deal to me. Open interval means do not include the endpoints. Closed interval means do include the endpoints. These confidence intervals are just approximations anyway. So it's not really a super big deal if you include the endpoints or not in your answer. The variable's continuous. It's not a super big deal. I shouldn't say equals here, but I'll say or. And so what do we say? How do we interpret this? We say we're 95% confident that the true population proportion of robots used for loading and unloading is between 18% and 30%. Does that mean the probability that the true proportion is in there is 95%? Technically, no, because you've done your sampling, all the probability is gone. If you had a different sample, think about this logically. If you had a different sample, you'd get a different answer. And in this case, not just for the point estimate, but also for the margin of error. If p hat is different, both of these things will be different. You'll get a different answer. Which one's right? They're both right. Which one contains p? Probably both, possibly neither. You don't know. It's just inherent in the subject that you don't know for sure. If you do repeated random sampling, many samples of size 200 from the same population and get many values of p hat and many confidence intervals that are 95% confidence intervals, about 95% of them will contain p, though you won't know which ones do and which ones don't. So you might be able to say if one seemed like it was a big outlier, that you might look at that and say, well, that's a big outlier confidence interval. I'm almost positive that p is not in there. And that can happen. Though on the flip side, people rarely do repeated sampling, right? The goal is to do just one random sample and get one interval, because you just don't have the time or money to do more than one. You just do one and you just hope. Pray if your job depends on it. Part B says, would you be surprised to hear someone claim that the majority is used for loading and unloading? Majority means bigger than 50%. This interval is far from containing 0.5. Yes, you'd be surprised. So what that hints at is that intervals, confidence intervals, can actually be used for hypothesis testing. Though to be truly accurate in terms of relating it to the alpha here, it technically needs to be a two-tailed test. If I was doing a hypothesis test that the null is 0.5, the majority is that it's bigger than 0.5. But if I was just testing to see if p is 0.5 or not, a two-tailed test, I'd be inclined to say that since this interval doesn't contain 0.5, and you might even say for extra emphasis, since 0.5 is not even close to being in the interval, that I definitely reject the null here. But to be truly accurate, even for example, in the case where the null were say 0.31 instead of 0.5, close to being in the interval, the alpha that you would have to use, well, the alpha that we used for the confidence interval, in this case 0.05 right there, would be the same alpha that you'd have to use for the level of significance for this test. In other words, to say that the confidence interval rejects the null when the null value is not in there is equivalent to saying it rejects the null when alpha is 0.05, if you were doing the hypothesis test, but only for a two-tailed test, technically speaking. I know that's not easy to digest in 1 minute there, but we'll talk about it more. It's not in your test. We'll talk about it more next Tuesday. You can do pure hypothesis testing problems as well. Well, there are also problems about how large a sample size should you have to get given margins of error. I'm going to skip this problem for the moment. That kind of problem is important for designing samples, deciding how big the sample should be, for example. Let's end class today with this problem. A new computer network is being designed. The makers claim that it is compatible with more than 99% of equipment already in use. Wow, that's a large null value that we're going to end up using there as a percentage. It's compatible, that's the claim. It's compatible with more than 99%. By the way, there are different formulas for confidence intervals besides the ones I'm teaching you. In this context, there are actually other formulas that give you different intervals, and some statisticians think they're better. There's something called a Wilson estimate that many statisticians think work better, especially when P is close to 0 or close to 1. I'll just leave it at that. There's debate about the subject, okay? Statisticians debate each other about what's best, because it is more of a scientific kind of approach to things rather than a mathematical deductive approach to things. We want to set up alternative hypotheses to support the claim that it's compatible with more than 99% of the equipment in use. So the alternative is that P is bigger than 0.99. And while that's a very large null value, 0.99 in this context, right? You can't get bigger than 1. So right away, I'm looking at this problem and I'm saying, is this even a valid kind of hypothesis test to do? Because the null value is so close to 1. Even if we can reject it, is it important to reject it? Now, the company might say, yes, they want to prove their claim. So they want to reject it so they can say in their commercial that it's compatible with more than 99% of the equipment in use. A sample of 300 programs is run and 298 run with no changes, so it's compatible. Can the null be rejected based on the p-value? 298 out of 300. P hat is bigger than 0.99. P hat is 298 out of 300. That is bigger than 0.99. So certainly for this sample, we get something bigger than 0.99. But the question is that enough bigger than 0.99 to feel confident rejecting that null hypothesis? That's always the question. It's a statistically significant evidence against the null hypothesis. And we're out of time. I'm not going to finish the problem, but I will say what you would do is you'd compute a z statistic looking like this, where P0 is the null value. That's going to be 0.99. And if this z statistic is extreme in the positive direction, because it's a right tail test, if the p-value is small, we would reject the null. But to tell you the truth, I question whether or not such a hypothesis test is even valid, because our null value is so close to 1. Is this even a valid thing to do? So this kind of problem will not be on the test, but it will be on some things to work on after next class, possibly over Thanksgiving, or you can do it before or after Thanksgiving.